All right, here we are again. So I didn't want to take any chances today. It looked like the weather was going to be pretty foul out there. So what the heck? This is our first and hopefully last online session of the semester. So today we'll be doing things a little differently. First of all, we're going to be doing chapter 8. And because we're completely done reviewing for the midterm, all the problem sets are taken care of for chapters 5 and 6. The midterm, a sample midterm is done. All the solutions have been posted. So all that's left to do is carry on with the new material in chapter 8. And then a week from today, we'll have the test in the classroom on chapters 5 and 6. Okay. So, but for today, we'll be doing something a little different. And also, I just want to point out that since we're online, this meeting is being recorded. You'll be able to look at the video when it's done. And because Moodle doesn't apparently have a lot of capability for storing videos, they've asked us to put these on someplace else, which in my case happens to be YouTube. So if you go to my YouTube account, or if you go to YouTube itself, and all you have to do is find or type in my name, and it'll say, oh, I know where you want to go. And you can see here, it's already set up, of course. And then what you'll see is that there's all the videos are along here. There's a bunch of videos from all these different courses that I've been doing over the last few years, but I'll be setting up a separate playlist just for this class so that you can find it more easily. So if you go into the playlist, you'll see later on today, there'll be a playlist set up for just this class, and you can go find the video without having to sort through all of them. And there's so many of them here. It really piled up over the last few years. So by the way, they're all publicly available. If you really want to learn more about something else in the area of math or economics or statistics, go ahead, be my guest. You can look at all of them. They're all publicly available. I typically get 2 or 3 people reading each one who are not in the school. I don't know how they find them, but they do. And so anyone who wants to read or look at any of these other videos, that's perfectly fine. So anyway, in the meantime, let's get to this chapter 8 and see what it's all about. All right, so, one more thing too. If you notice on the slides that I'm showing you here, the slides are on Moodle, but during the 8:30 class, I added some more handwritten notes to these slides, and I'll be doing the same thing here. And so I will also be posting these handwritten notes onto Moodle as well. So there'll be 2 different versions of the slides, the original, and then the one that has all the extra little notes that I put in here. Okay, because as we went along in the 8:30 session, I added a few more examples and I didn't want to lose them. So you'll have access to both of them on Moodle. Anyway, what are we doing in this class, or this chapter rather? The title of the chapter is Consumer Math. Primarily what it's focused on is interest rates. Okay, now this is meant to be a very applied chapter. In fact, it's meant to be very useful because sooner or later, one of these days you'll graduate and you'll hopefully have plenty of money. And so much so that instead of spending it all on living expenses, you'll actually have some money to save and invest. And when that happens, you'll have to understand a lot of important details. For example, what investments are out there, or in a more basic level, what kind of products are available for savings. Like, for example, there are different kinds of savings accounts. You could also have a checking account, but there's a lot of other choices as well. But in many of the cases, the rate of return will come down to the interest rate that's being offered to you by that account. So, for example, if you walk into a bank right now and say, I want to start up a savings account, they'll tell you what kind of interest rate they're paying on their savings account. Now, at this point in time, interest rates are unusually low levels by historical standards. So don't be surprised when you hear them tell you that, let's say, the interest they're paying on a savings account is probably less than 1%. Historically, you could have gotten 3, 4, 5% on one of these accounts. But at this point in time, interest rates are very low, which is not so good if you're a saver. But if you're a borrower, if you're trying to buy a car, let's say, then that's a wonderful situation because the cost of borrowing will be very low. Okay, so right now rates are low. They'll probably end up going up a little more this year. and in the near future. But what's important to understand is how much am I earning when I put money in a savings account, or how much am I paying when I borrow money for, let's say, to buy a car or a house, or even to use a credit card. Okay, so all this information is very helpful for you to know. And the more you understand how this works, the better decisions you'll be able to make with how to manage your money. Okay, so it's really an important topic. Now, at some schools, they offer a course called personal finance. And in a course like that, you would actually spend the whole semester talking about these types of products that are available. So I don't know if they offer it at purchase or not, but if they do, you might want to at least look into it, because it could be potentially very, very helpful to you when you graduate. Here, we're really more focused on the mathematical content of it, but just keep in mind, all of this is very important because it'll help you understand what you're doing in the future when you're either borrowing money or saving it. You do have one. All right, well, that would be good. At least investigate it. If you might have a free elective coming up your way in your schedule, and at least take a look at the schedule and see what they're going to talk about, because it's potentially very, very important. The kind of things that you're not likely to be, nobody's going to take you aside and explain any of these things to you. It's something you have to pick up on your own. And if you don't understand how these things work, it could end up costing you an awful lot of money. So yeah, it's something to think about. All right, let's put it that way. Oh, it was either that or this. Well, that's different. Okay, well then okay, let's just say this is a good choice then. But for anything else, that might have been a better choice. All right, so in other words, let's say this is number one, that's number two. How about that? All right. So anyway, what are we doing here? Well, we're starting out by defining different types of interest, and we're going to see how they're calculated. So we'll start out with the case of what's called simple interest. Now, interest, as you know, is what is charged on a loan, or it is what is paid to you when you save money in, let's say, a savings account or a checking account. There are different kinds of interest. We're going to focus on simple interest, and later on we'll introduce what's called compound interest. Most of the time when you borrow or lend money, you'll be paying or earning some combination of both. It's very unusual that you only do one or the other. So most of the time, there will be simple interest involved as well as compound interest. Now, in order to understand what we're doing in this section, we need to introduce a handful of very important variables. Let's take a look at them right now. For example, we're going to use the letter P to represent the word principal. And this is the amount that you're either borrowing or lending. So in other words, if you decide to buy a $25,000 car and you get a loan from the bank, then you're borrowing $25,000. The principal of that loan is $25,000. Or if you put $1,000 in your bank account, that is also considered to be principal, because that's the amount that will be used to determine how much interest you earn during the year. Now, of course, central to all of this is this notion of an interest rate. And you notice I've circled the word rate because I want to make it clear that this is a percentage of some kind. Let's say, for example, you find a bank that's willing to give you 6% for keeping your money with them. Well, they would give it to you, or it would be written as either 0.06 or 6%, because they both mean the same thing. Okay. Just remember, 6% is simply a shorthand that actually represents the decimal 0.06, or 6 out of 100. This is, by the way, this is understood to be quoted on an annual basis. So in other words, if I'm borrowing at this rate, I'm paying 6%, not total, but every year that the loan is still outstanding. So there's always a time element with interest rates. It's so much per year. All right, now what else do we need to know? Well, we need to know the time involved with whatever we're doing. In other words, if we're lending money or borrowing money, it's important to know how long this will last for. So we call that the time or the term. And this is expressed as a certain number of years, or if it's less than a year, a fraction of a year. So we're not going to think about this in terms of months, let's say. It'll be years. And now here's the interesting one. Suppose if you look at the top, I've written this small example here. If I put $1,000 in a bank right now, and suppose after a year, I find myself with $50 worth of interest. You can see in the bottom here, I've circled the word I for interest. We don't want to be confused here between this R and this I. This R is a percentage. It's called an interest rate. Okay, this I is a dollar amount. That's the dollar value of the interest that I'm being paid by the bank. So in my example on the top here, I'm assuming that that's $50. And so what that tells me is that at the end of the year, the total balance in my account is $1,050 because I still have the original $1,000 principal, plus I've earned another $50 worth of interest. So now all of a sudden I look at my account and it says 1050 instead of 1,000. So that's because the first 1,000 is my principal, the rest is my interest. So that $50 is what we're going to call I. The A is something new. This is something called the future value. In other words, how much will my account be worth in the future? And that, we'll see how it's calculated, but basically it represents the sum of my principal plus the interest that I earn. So the future value is often what we're really trying to figure out. We're trying to find out, for example, if we put X dollars in the bank now, how much will it be worth at some point in the future? So that's often what we're really interested in finding out. It helps us with our long-range planning, of course. If you have decided that you cannot retire until you have $1 million in the bank, well, then you'll need these calculations to help you figure out how long that will take to happen or how much you have to put in the bank in order to have this in a certain number of years. So this is a very important idea, but really all it represents is the sum of what you put into your account plus all the interest that you earn over the years. Now, I did mention before that there's two different kinds of interest. We'll start with the case of simple interest. So simple interest, what makes it simple is not the formula, although it is a very simple formula. The fact is that with simple interest, the entire amount is calculated based on our principal. How much do we put in our bank account? So the formula is very straightforward. I, the simple interest, equals the principal times the rate of interest times the time over which I deposit my funds. All right, and so the entire amount is based exclusively on how much principal did I start with. And then of course we have to take into account the interest rate and the time, but this is what we mean by simple interest. And again, and in this example I showed you up here, this I is simple interest because it's entirely based on the $1,000 that I started out with. But this formula, as you can see, is very, very easy. Not only that, but we'll be able to use it for different purposes, as we'll see in a few minutes. So it's a very flexible formula. We'll get a lot of use out of it. And it also doesn't hurt that it's so easy. We like easy formulas, I think. So let's just say that we have a case where an investor deposits $1,000 for 1 year in a bank account with the rate of interest, which is R, by the way. Let me just put that in here somewhere. Okay, 3%. So how much simple interest should we expect to earn during that year? Well, let's come down here and write PRT. The principal is the original $1,000. R is the rate of interest from here. 1 is here because we're leaving the money in the account for 1 year. So at the end of the year, we should have $30 worth of simple interest. And then at the top, I've added to it the fact that the future value, actually, I could put it probably right here. The future value of my deposit would therefore be $1,030. It's that simple. Okay. Now, what if I'd left the money there for 2 years? Well, the calculations are very simple. All that would have changed is that instead of T equals 1, I've got T equals 2. So after 2 years, without adding any new money, by the way, I'm going to wind up with $60. So it's just $30 every year is my simple interest. All right. So far, I think we understand what simple interest is. It's just the interest that is being accumulated or paid to the depositor in exchange for leaving P dollars in that bank account. And yes, now this future value concept, you can see that it's a very simple idea. If you just simply take your principal and your simple interest, you'll end up with A, which is our future value, remember. But there's an equivalent way of calculating it, which we'll put to good use in a few minutes. Because if you remember, if I equals PRT, then this formula actually is the same as saying P plus PRT. And I can factor out that P and end up with A equals P times 1 plus R times T. Now you might say to yourself, well, that looks even messier. Why do we want a messier formula? You'll see why in a few minutes. Okay, it's very useful to express it this way. All right, A equals P times 1 plus RT. It means the same thing, but you'll see why it's so helpful with the next example. All right. So, by the way, what if we put our money in the bank for less than a year? Well, then the T, remember, T represents time in years. All we have to do is let T represent a fraction of a year. So let me show you what I mean by that. What if an investor puts $1,000 into a bank account for only 6 months and the bank pays 4% per year? Well, T could then be thought of as a half a year. 6 months, half a year. We replace the T with 0.5 now. And when you plug in this formula, you'll see that this investor will actually end up earning $20 worth of simple interest. Even though it's a 4% rate of interest, the money was only deposited for 6 months. And so therefore, it's only $20 rather than $40. And so the way we determine that, again, is to let T be a fraction of a year or 0.5. All right. So now I did mention a little while ago that this simple interest formula is very flexible. What we can actually do with it is we can take it and rearrange it algebraically to solve for any of those 4 terms. Okay. In other words, right now, the way it's written, we're being asked to solve for I, the simple interest. But we could also use it to solve for P, the principal, R, the rate of interest, and T, the time, if we need to. Okay, so let me show you how that would be done. Let's start with the principal. So if I take that equation and rearrange it algebraically, what I can actually do is divide both sides by RT. And you can see I'll end up with P equals I over RT. Why would I want to do that? Because I may need to calculate the amount of principal that somebody has borrowed or lent based on the amount of interest that they're being paid. So let's try an example of this. And again, you can see it's a simple algebraic rearrangement. There's nothing to memorize. All right, so for example, what if a homeowner has borrowed from a bank to finance various repairs, and we determine that the simple interest is $20,000, the rate of interest is 4%, and this is going to be paid back in 5 years. With all that information, we'd like to know how much the homeowner must have borrowed in the first place. Or in other words, what is the principal? So we've got the variables up here. I is 20,000. Oops. The rate is 4, and it's a 5-year loan. So I repeated the formula here. Now, I'd like to point out, though, that on your calculator, if you're going to plug this into your calculator, the parentheses must surround the entire denominator. So what you're actually going to do is type 20,000 divided by, and then in parentheses, you'll have 4% times 5, close parentheses, equals. And that should give you the answer. Now, I'm going to double check that with mine. Because I always want to make sure all those equals are absolutely necessary whenever I use this calculator. 20,000 divided by open parentheses, 0.04 times 5, close, equal. Yeah, that'll do it. If you don't do it this way, if you're not careful, if you don't use the parentheses properly, you certainly will not get the right answer because of the order of operations. And therefore, we end up, as it turns out, because this actually turned out to be 20,000, 0.04 times 5 is 0.2. And that ratio is 100,000. So that tells me that the homeowner would have borrowed $100,000 in this case to fix the house. All right, well, if we can solve for P, let's go back to this formula again. So now I know how to calculate I. God, what happened? Hold on. I equals PRT, right? So I've solved for I, I've solved for P. Why don't we now try to solve for R and T? Let's start with R. All I have to do is rearrange algebraically, divide both sides by the PT, and what's left behind is the value of R. I was just wondering if anybody has any cool screensavers going on here. Okay. No. It looks like everyone's camera shy today too. That's okay. Oh, there you are. Hello, how's it going? You're allowed to eat in the class. Well, what is that? Is that your red pen?
This is a pencil, and then I have a coffee cake and orange juice.
Oh, nice.
Yeah. I was unaware that we were online today, so I found out I was in the middle of Einstein.
It was a last minute thing. I looked out the window yesterday, actually, and I said, by the time it gets to be tomorrow morning, those roads are going to be solid ice. And I was just like, well.
Incorrect. It's like 45 degrees.
Is it? Oh, my God. Oh, well, what are you going to do,
I was worried about you. My roommate was in your class yesterday, and you didn't show up.
Yeah, you know what happened?
I was scared.
Yeah, you know what? I'll tell you what was happening. I decided, okay, let's do online, because yesterday it was really bad out. So I went to Heliotrope, and there's this little button that says, click here to email your entire class. So I did. I sent them an email, and then about 2 hours later, I sent them another one. I said, let's do online because the roads are scary. It turns out that the damn thing didn't work. And so nobody got the message. I'm like,
yeah,
what the hell? I'm the most skeptical person in the world when it comes to technology, but you figure when the button says, send the class an email, it will send out an email to the class.
Yeah, no.
So I guess I'm just not cynical enough about the technology. It's just unbelievable. So anyway, after the fact, I was able to write back to them and say, listen, here's what happened. It was really annoying. And then, because I guess I should have figured when nobody signed in, but I went ahead and I did the entire class. I recorded it for them and I did everything, but I was really irritated. I actually wrote to the school and said, what the hell? And so we'll see how they react to that. Very, very frustrating. It's like imagine if on your calculator it says multiply and it actually divides when you hit that button. It would be something comparable. So, but that's the way it is sometimes with technology. You should never depend on it, ever. So anyway, so let's do the R. So this time, oh, by the way, we're going to see this example a few times. A CD or certificate of deposit is a special type of bank account where you keep your money in the bank for a fixed length of time. And in exchange for that, they give you slightly more interest than you would get with a regular savings account. The only problem is you're committing yourself to leaving it there for that whole, in this case, the whole year. So, you know, you want to think about this. If you're sure you don't need the money, it's a great way to earn a little more interest. But if you do need the money, whoops, what'll end up happening is that they'll give it to you, but they're going to charge you an enormous penalty, which essentially wipes out all of your interest and then some. So this is something we want to be careful about. But imagine that you are actually doing this and you're going to earn $20,000 worth of simple interest. What rate of interest are you being paid? Well, all we have to do, as you can see here, is rearrange this algebraically. And so you're going to take 20,000 divided by 1,000,000 times 1. Now, again, you want to be careful. Whoops, Jesus Christ, I just lost my marker here. I can't write on the screen without my special pen. It seems to have rolled away from me. Oh, here it is. I couldn't see it because it's black and it's sitting on a black keyboard. So what you should do is type 20,000 divided by open parentheses 1,000,000. By the way, I don't think you're supposed to use commas on this calculator. It might show them, but I think you're not supposed to type them in as you're typing. So let's not do any commas. So here's the key. Now, of course, in this case, you're multiplying by 1, so it hardly matters. But in general, you want the entire denominator to be surrounded by parentheses. Otherwise, again, you'll get the wrong answer. And it turns out to be 0.02, which we know is the same thing as 2%. Now, by the way, there is a button on your calculator. I'm sure everyone understands how interest percentages work, but just to be on the safe side, sometimes when you get really small numbers, it might get confusing. Let's say that you aren't sure what is the decimal equivalent of 2%. On this calculator, if you type the 2 and you follow it up with this little button that's directly over the 9, it'll actually convert it without the equals into 0.02. Okay. And like I said, for 2, it's pretty straightforward. But what if it was like 0.92%? It's easy to make mistakes. So therefore, just in case it's there, I don't think it'll go the other way, though. I don't believe it has that capability. But just remember, all you're really doing is you're dividing by 100. When you go from 2 to 0.02, in fact, some people have suggested that the origin of the symbol is that all it's really doing is telling you just a rearrangement of the digits in 100. Ooh, that's interesting. That could be. Sometimes we use these symbols all the time without necessarily knowing what their origins are. Might be interesting to investigate. Imagine if you had time to write a book. Would you choose to write about symbols and how cool they are and where they came from? Would that be your book? No. All right. Well, let's say you had time to write 10 books. Could that maybe be your 10th book? No. How many books would you have to write before you got down to this one?
I would develop carpal tunnel
before
I wrote that book.
Okay. Okay. But it could be done. It might be fun. All right. Well, anyway, now the last thing we want to do is the time or term. So algebraically, again, I can take my original expression and rearrange it to solve for t by simply dividing out the p and the r. And this is kind of interesting because you might be able to figure out, for example, how long will it take you to have earn a certain amount of interest in your bank account. So there's a lot of potential applications for all of these formulas with long, when you're trying to plan your finances, you're trying to figure out how long you have to save to buy a new car, for example, this all comes in very helpful. Now, of course, in this day and age, you can probably just get on the computer and, there'll be a website somewhere that does this automatically, but you want to make sure it's doing this correctly. You know what I mean? You can't really just assume that it's been set up correctly, but they do exist. Like if you suddenly decided one day, I want to buy a car, there's a website out there somewhere there. All you have to do is tell it how much you want to borrow, how many years you want to pay, and what rate the bank is charging. It'll figure out the payments for you, no problem. But it would be nice if you could do it yourself to confirm that you're doing it correctly. Anyway, so imagine here now, the investor is putting 100 grand into a CD that pays an annual rate of 3%, and the investor will earn $30,000 in simple interest. So we already know that P is 100,000, R is 3%, and I is 30,000. What is the value of T? No problem. We have this amazing formula here. And so you can see, work out the numbers, and on the calculator, you should do 30,000 divided by, open parentheses, 100,000 times 0.03, close equals, and it'll turn out to be 10 years. Okay, so this is a 10-year CD, and over that time, we will accumulate $30,000 worth of simple interest. Very good. All right. So all of these examples we've seen so far were based on the premise that we're looking at just simple interest. So that raises a good question. What is the other kind of interest that we might earn or pay when we borrow or lend money? And that is the more complicated one. And it's called compound interest. And what happens here is that you're paying interest on interest, or you're receiving it. So I was saying to the other class that this is how people get into trouble with credit cards, because when you don't pay the entire balance every month, interest piles up and is added to the principal that you owe. So you end up paying interest not just on the amount you charged, but the amount of interest that they charged you by not paying off your balance. So compound interest is an important component of any investment, or the amount of interest that you'll end up paying when you borrow money. It's more complicated to calculate it, but luckily we have some formulas that will help us with this. Okay, so, and again, just to summarize, the two basic types of interest that we will encounter here are called interest on principal, or simple interest, and interest on interest, which is compound interest. All right, now, what we're going to do is introduce this concept of compounding frequency. So imagine, in these examples we've been looking at, we've been assuming that interest is paid at the end of every year. You put your money in the bank today, a year later, you get interest on it. What if it doesn't work that way? What if instead the bank pays you interest twice a year, or they charge you interest twice a year in a loan? What would that do to our balance in our bank account? So let's say, for example, there's a bank that pays a 4% interest rate at the end of each year. Actually, let me type this. It's a little easier to read it. So suppose a bank pays a 4% rate of interest. Okay. And an investor or saver deposits $1,000 for a year in this account. How much will he have at the end of the year? Well, we already know. Oh, we can figure this out ourselves. 1,000 times 1 plus 0.04 times 1. Because remember, R is 4%, T is a year, to end up with $1,040. Now, this is something we haven't done up to this point. Let's break this down a little bit. Hold on. Of this $1,040, 1,000 is principal. $40 is what we'll call total interest. But let's go back for a second here and remind ourselves that in this case, I equals PRT. That equals what we call simple interest. Now, it turns out that if that's the case, since all of the interest is simple interest, the compound interest is zero. There is none, okay? So in this very simple case, there's no compound interest. But what we're going to do now is change the assumptions of this problem. Suppose instead of paying 4% at the end of each year, the bank pays 2% at the end of each 6 months. What will be the future value of this $1,000 deposit? All right, so after 6 months, how much will we have? $1,000 times 1 plus 0.04 times a half a year, 1,020. All right. How about the next 6 months, though? Now, this is where it gets interesting.
Professor, I hate to interrupt, but I know that you're kind of a cat guy, right?
I am a cat guy.
All right. Well, if you'd like to see, my roommate's cat is paying a little visit.
Oh my God. Hello.
Hi, this is Onyx.
I'm kind of surprised that he hasn't jumped in front of your camera yet.
She is not people friendly.
Okay. 'Cause I get this all the time. When I was doing online constantly, anyone who had a cat, sooner or later, the cat doesn't like being ignored and they will jump on top of your keyboard. And I get a good hard look at it, you know, like, oh, look at the cat. He's so big and fluffy. And oh, they don't like being ignored one little bit, do they?
Well, she's also not mine.
Okay, well, that too. If that was your cat, she'd be.
If it were my cat, she's an attention whore, but she's not mine. She's also not really in the common room much because one of our roommates is very scared of animals.
Oh, okay. All right. Well, then she's very pretty, though. But surprisingly reluctant to jump in front of your camera.
I know, right? It's so weird. But I'm also using my phone, not my actual laptop. She has put herself on my laptop before.
Okay, that probably has a lot to do with it too, because you
Absolutely.
can't see what you're doing. Yeah. Okay. Explains everything. All right. So now here's what we really want to know. So you got 1,020 after 6 months. What happens after another 6 months or by the time the year is over? This is by the way, this is the key to everything we're doing today. After 12 months or 1 year, we're going to use the same formula, but guess what's different? Instead of starting with 1,000, we now have 1,020 at the end of the 6 months. So all of a sudden, that interest is being applied both to our $1,000 principal and the first $20 worth of interest. So all of a sudden, instead of ending up with $1,040, we have 1,040. So you can see something changed. Now that's the light bulb is going on moment. That is why the result is different, because during the second 6 months, the interest was credited or based on not just the principal, but the interest from before. So that last 40 cents is known as compound interest because it is based on previously earned interest. So this is important right here. That's why I put the red in there, so that when you go and look at it again later on, you'll say, I get what's going on here. So, wow, that was a huge breakthrough. Now, that being the case, we can summarize the results a little bit here. I just wanted to wrap this up here a little bit so that we can look at some more complex examples. But with annual compounding, we only had $40 worth of simple interest, which is our total, and therefore our future value was 1040. Remember, there was no compound interest. Now, look what's different. You got 40 cents worth of compound interest. And now, of course, it's only 40 cents, but the grand total of interest goes up to 4040, and therefore the future value goes up to 1040.40. Now, again, it is a small amount, but that's interest that you would not have gotten if we had annual compounding. Okay. So now that raises an interesting question. What if instead of paying the interest twice a year, 4%, rather 2% twice a year, what if we split it up into 4 parts? What if the bank suddenly decides, let's pay 1% each quarter for the next year? What would that do to our results? Well, let's see. So I went through the same calculations. And again, I've highlighted the important parts. You can see that after 3 months of $1,010, and now after 6 months, some of the interest you're earning is coming from that last $10 worth of interest. And that means that, oh, look at that. I've got $1,020 and another 10 cents. That last 10 cents came about because it's credited to this $10 worth of interest. Now I'm going to do this 2 more times. Each time, if you notice, I'm taking advantage of that wonderful formula from before. A equals P1 plus RT. So if I do this twice more, once for 9 months and once for a year, look what happened. At the end of the year, instead of $1,040.40, now all of a sudden the total is up to $1,040.604. Again, we earn more what we call compound interest. The first $40 is still simple. That will never change. It's this part that's changing, the last part. And as you can probably guess, if I keep increasing the frequency of the interest payments, this compound interest here will keep going up. So even though the simple interest never changes, the total is going up. So as a lender, this is making me very happy, because it means I'm earning more interest for the same amount of money that I put in the bank. So to summarize this one, simple is 40, the compound is 60.4 cents. This is the total. And so therefore the future value is the original 1,000 plus my interest. Ooh, that's interesting. So now we're not going to do any more of these just now because this takes a while, but we can do this later on with one of our formulas. So what I wanted to do here is show you a very important set of conclusions from all this. And that would be that as the compounding frequency, which by the way, simply means how many times a year I pay the interest, as it keeps going up, the simple interest never changes. The compound interest continuously increases. So therefore the total interest must go up. And so does the future value. There you go. So it's all this increase in interest is coming from that compound interest. So, oh, what's going on? Okay, so that's the grand conclusion. Now we're going to prove it with some more examples, but this is really the heart and soul of what we're doing in this section. So remember, the compounding frequency simply means how many times a year is the interest paid. We saw examples of annual or once a year, semi-annual, twice a year, and then finally quarterly, which is 4 times a year. We can keep pushing that too. There's nothing to stop us from compounding interest every month. And ultimately, there's nothing to stop us from compounding it every day. Now, you might be surprised to discover that this is exactly how it works with banks. When you put your money in the bank, the interest is being credited to your account every single day, which works in your favor if you're saving money. But if you're borrowing money, like with a credit card, well, it's just the opposite. It's going to cost you more interest if the compounding frequency is very high. And by the way, when you get a credit card, I'm sure some of you have a credit card. When it came in the mail that first time, you're all excited. You probably didn't even look at it, but there was a legal contract that came with it, a really thick document with the tiniest imaginable print. And somewhere buried in the details there, they would have told you how often the interest is compounded because they have to by law. And so if you go find it, you can dig through the drawers and see if you kept it. It'll say in there somewhere almost for sure that they're compounding your interest every day. Okay. But when you go to the bank to deposit money, it'll be the same thing. So in most cases, in the United States at least, the compounding frequency is daily. There could be some situations where it's not daily. Certain types of loans, certain types of securities that you can buy in the market. But for simple cases like savings accounts, checking accounts, certificates of deposit, car loans, mortgages, it'll be daily. All right. Now, there's a formula that will save us from having to go through all these steps. Like with this example, it was interesting. But if I wanted to see what happens with monthly compounding, that could have taken me a long time. So instead, we'll use a formula. So here it is. And believe me, it looks scarier than it is. Okay. Every term in there you've already seen, except for N, that letter N represents how many times a year is interest paid or credited to your account. In other words, it's the compounding frequency. All the rest of these terms you've seen before. Okay, so there's nothing mysterious about it. But keep in mind, this is a more complicated version of this one. The one we had earlier only works with simple interest. This one you can use for any situation. So we'll basically be sticking with this one from now on. And remember, future value simply means how much will I have in my bank account in the future, given that I've deposited P dollars for T years with interest rate R and compounding frequency N. All right. Now, I have a chart on the next page which shows you what to do about the N. So let me just flip ahead to that. So for example, with semi-annual interest, you would have n equals 2. For quarterly, you can see up here, it's 4. Monthly would mean n equals 12. And then finally daily, it's 365. You won't, it's not likely you'll run into any other frequencies. Those are the standard ones. But like I said, most of the time we'll be using daily. All right. So now, based on these examples, what we're going to do next is we're going to essentially rework them by using this wonderful new formula. And we're going to get some nice practice using this formula, like I said, that at first glance appears to be scary, but there's a trick to it. I'm going to show you how to streamline it a little to make it less likely that you'll make mistakes. So let's say we'll start with the same situation. An investor deposits $1,000 into a 1-year CD. The rate of interest is 4%, but now we're going to calculate the future value based on 4 different assumptions about the compounding frequency. We'll look at annual, semi-annual, monthly, and daily. Okay, but this time we're going to use the formulas, the big formula. All right, so this means that P is 1,000, T is 1, and R is 0.04 for 4%. So what's going to be different in each case is N. Okay, now let's start with the first case with annual compounding. So there's your formula. And you can see we plugged in all the numbers. 1,000 is your principal, 4 is your interest rate, 4%. N is 1 because it's annual compounding. And it's only a 1-year investment. In all of these cases, T will equal 1, by the way, because it's a 1-year investment. So basically, this is a simple case because you can see what's in the parentheses reduces very nicely to 1.04 to the first power. And you can easily multiply that out in your calculator, and you'll see that we get exactly the same results from before. The future value is 1,040. 40 of that is simple interest. There is no compound interest. Okay, so we already knew that, but we calculated it in a different way. All right, so we're off to a good start. Now, let's complicate it a little and have semi-annual compounding, which we already know what the result will be, but let's take a look. So here, now this is my idea for making this less difficult to make mistakes. Why don't we reduce this? Instead of leaving it like this, just simply rewrite it as 1.02 raised to the second power. And then multiply that by 1,000. I think that's the quickest way to get it done without making a lot of mistakes, because if you go from left to right like you're used to doing, you'll need multiple parentheses, and that's likely to lead to mistakes. So down here, I've sketched out the steps. You would put 1.02 squared. I've used the exponentiation function here, equals times 1,000 equals. And if you do that, you should see the same result we had before, $1,040.40. All right, so you already knew that this was the answer. It's just that now we've obtained it with this amazing formula. And of course, we always want to be able to decompose this into the amount of simple and compound interest, which is easy because the simple interest is always 40. Okay. The rest has to be compound interest. So in other words, 1,000 is principal. The remaining 40.40 is interest. 40 is simple interest. Now, by the way, I did that up here on the top the simple interest is I equals PRT. So for these examples, the simple interest will always be 40. So that means whatever's left has to be our compound interest. So if you notice, we're not directly calculating the compound interest. We're figuring out what the total future value is, subtracting the principal so we can figure out what the interest is. And since we already know what the simple interest is, whatever's left over again must be our compound interest. So it went from 0 to 40 cents. Now, this one we haven't seen before, monthly. Now, here, unfortunately, this one needs some rounding. 4% over 12 is not an even amount. You can type this as 1.0033333, okay, and you'll get the right answer. Another option you have is to actually do the calculations yourself. So I'll put this on the bottom here. 0.04 divided by 3 equals plus 1 equals raised to the 12th power equals times 1,000 equals. If you follow those exact steps, you'll get the right answer without having to do any rounding. So let's say it annoys you that this might be imprecise. Not a problem, because then this way in the bottom, you've got the exact, and I mean the exact values. One thing I do want to point out too is that because this is money, you don't really need any more decimals after the first two because the bank will round this for you. They're not going to give you 74 cents and a fraction. It'll be 74 cents. So you don't need to overly round it. You don't need a huge number of digits here. But if you notice, remember the last case, the compound interest was only 40 cents. Now it's 74 cents. What happened? Well, because we increased the frequency from 4 times a year to 12 times a year, the compound interest went up quite a bit, didn't it? Yes, it did. Wow. So I've saved the trickiest one for last, daily. Now, of course, there's hardly, when you're doing daily interest, the amount per day is quite small. So we have to be very careful with this one. And you can see that 0.04 over 365 is approximately 0.000109. Yeah, 589. Look at that. What a mess. On the bottom here, though, I'm showing you how to get the exact value by actually dividing 0.04 by 365, adding the 1, raising that to the 365 power, and then finally only at the end multiplying by 1,000. And you can see this time the compound interest is 80.8 cents. So what's interesting about this is that at first the compound interest increased very quickly every time we increase the compounding frequency, but then it seems to have slowed down a bit. The difference between monthly and yearly is not very much, is it? No, it's not. Okay, it's kind of a strange relationship. What's happening is that the compound interest is increasing at what we call a decreasing rate as we increase the compounding frequency. So now here's what I've done for you. Just because I like seeing everything nicely organized in a little chart, a chart that summarizes our results. Well, guess what? I put it all together for you so you can see them all together in one convenient slide. Okay. And that way you don't have to keep going back and forth and flipping through them over and over again. Here it is. Now here's what I've done. On the first column, I've got the frequencies, and that includes the quarterly case that we saw earlier. You can see at a glance, the simple interest is always 40. The compound interest we calculated in the slides. And if you notice, at first it goes up very quickly, and then it starts to go up very slowly. The total interest is here. This is the sum of these two. The principal is just 1,000, that never changes. And then the future value is simply the sum of the interest and the principal. So that way you can see at a glance how these different variables are influenced by the compounding frequency. Huh. So now you know. So now you're not likely to see the frequency go past yearly, by the way. I mean, sorry. Oh, I just realized I typed this in wrong. This should be daily. Well, that was a stupid move. All right. Yeah, that one is daily. And in fact, if you were to draw a little graph here, let's try this. It looks something like that. It increases fairly quickly at first, and then it sort of flattens off. So, and that's what you would expect because of the way the formula is calculated. So in other words, the difference between monthly and yearly isn't nearly as much between these two. It's only 6.8 cents compared to these two, where the difference is 20.4 cents. It's a big difference. And from here to here, wow, it's 40 cents. So as you in the low levels of compounding frequency, it makes a huge difference from one step to the next, but that gradually flattens out. Now, here's an interesting question. Here's one thing we have not done. So far, I just want to point out, all of the examples so far have assumed that the deposit, the bank deposit, was only for 1 year. What would happen to these results if the time or the length of the deposit increased? Okay, so let's say, for example, using the examples we just had, what if instead of 1 year, we went to, I don't know, 5 years? So the bottom line is that if, let's say if a 1 year deposit earns $40 of simple interest, a 5 year deposit would earn $200 of simple interest. It just goes up by $40 a year. The compound interest would increase far more rapidly over time. So in other words, it would go up by more, it would more than double every year is what I'm saying. In other words, instead of going from 40 to 80 to 120, et cetera, it would go up a lot faster than that. So because of that, what I've done is I put together a little chart so you can see this. What's happening here is I'm allowing time to elapse. And over time, the simple interest continues to increase at a fixed rate, $40 a year. But the compound interest, which starts out very low, starts to increase more rapidly. And at some point, it increases so quickly that your return mainly is coming from compound interest rather than simple interest. Okay, so, but this takes a very long time. It's going to take several years for this to happen, but eventually, if the money is saved for a long enough time frame, you're going to eventually earn more compound interest than simple interest. Now, we're not, going to do any examples like that right now. But all right, anyway, so I think this is a pretty good introduction to the topic. I don't know how I got ahead a little bit faster in this class than my other section. This is pretty much where we left off. So I guess there's no point in pushing ahead. I just want to keep both classes at the same point. So I'll tell you what we'll do, even though it's a little early, we can stop right here because we got a lot done so far. And we're going to come back on Monday and do a bunch of new examples. And then we're going to introduce a couple of new concepts. But I think this will do for now. And don't forget, though, of course, that next Thursday is the midterm. So Monday, we'll do more of this. And then on Thursday, we will do the midterm. Okay. So, all right. So if there's no last minute questions, I guess I'll just see you all on Monday.
Thank you, Professor. Have a good
Okay.
weekend.
You're welcome. Thank you. Bye.
Bye.
You're welcome.